So now we can finally find the rest of the eigenvalues. And in particular, the rest of the solutions to the characteristic equation. Because remember, we want to know when the characteristic polynomial is equal to 0. Well, that'll happen when either this factor is equal to 0, and that's going to happen when? That'll happen when lambda is equal to 4. So that's your first eigenvalue. That's the easy one compared to the other ones. That's the one we already found. Now what about that factor? When is that equal to 0? And well, this is not exactly something you can just look at and get the answer, but at least we can apply the quadratic formula. So let's do that down here. So lambda squared minus 4 lambda plus 1 is equal to 0. That'll happen, well, if you use the quadratic formula, that's going to be when lambda is equal to negative b. Remember the quadratic formula, right? Let me jot down the quadratic formula over here. So if I write the quadratic formula, it says the following. So ax squared plus bx plus c is equal to 0. That'll be true for the values of x given by negative b plus or minus the square root of b squared minus 4ac all over 2a. Right, so that's the quadratic formula. That's the one we're going to use over here. So b is negative 4, so negative b is positive 4. Then we'll have plus or minus the square root of b squared minus 4ac. So b squared is going to be 16 because negative 4 squared is 16. Minus 4 times a times c. In our case, a is positive 1 and c is positive 1. So 4ac is really just 4 times 1 times 1. And then our denominator, 2a, well, a is equal to 1 again, so we're just going to have divided by 2. And you can do the work, and this will reduce down to 2 plus or minus the square root of 3. You have to do a little bit of radical simplification to work on this, but you'll end up getting 2 plus or minus root 3 for that. So finally, that's how we can get our eigenvalues. So finally, we just have just enough room to squeeze them in down here. The eigenvalues of A are given by lambda equals 4, 2 minus root 3, and 2 plus root 3. So those are your eigenvalues. Finally, we got them. So the good news is that's about the worst case scenario as far as the workload goes for finding eigenvalues. But this problem threw almost every curveball at us that it probably could, but that's how you find eigenvalues. But it all comes down to finding your characteristic polynomial and figuring out for what values of lambda is the characteristic polynomial equal to 0. That's what it always comes down to. Okay, so let's look at another example, and just because the next example is not going to depend on this, I'm just going to move this out of the way because we don't need this anymore. Okay, so our next example is going to be another 3 by 3, but this one's a little easier, and we'll find out why in hindsight once we're done. So find the eigenvalues of this matrix. So our matrix is given as follows: 1/2, 0, 0 for the first row, negative 1, 2/5 for the second row, or in 0, and then 5, negative 8, and negative 1/4 for our third row. So that is our 3 by 3 matrix A, and we want to find its eigenvalues. Now there's some fractions in there, so be it. That doesn't mean we can't do it. Let's start by forming lambda I minus a, because that's what we're going to need to take the determinant of to find our characteristic polynomial. So lambda I minus a, in this case I is going to be the 3 by 3 identity. So lambda I is going to be like this: lambda, lambda, lambda down the main diagonal, and zeros everywhere else, and then we're going to subtract a from that. I wrote it a bit small, so I'm going to have to squeeze this in. Hopefully this looks okay. 1/2, 0, 0, negative 1, 2/5, 0, 5, negative 8, negative 1/4. So that is our lambda I minus a, and if we actually perform the subtraction, what will we get? We'll get lambda minus a half, and then 0 and 0 for the first row. Second row will be 1 lambda minus 2/5, and then 0. So that's our second row. So remember, that's 3 entries. 1, lambda minus 2/5, and 0. And then our last row will be negative 5, positive 8, and lambda plus 1/4. So that is our lambda I minus a, and now our characteristic polynomial will be its determinant. So what is P of lambda going to be? Well, the nice thing is this is a lower triangular matrix, lambda I minus a. So the determinant of a lower triangular matrix, and in fact an upper triangular matrix as well, is just going to be the product of entries along the main diagonal. And the first one on the main diagonal is lambda minus a half. Then the next one is lambda minus 2/5, and the third one is lambda plus 1/4. So those are the 3 factors of your characteristic polynomial, and the great news is this is already completely factored for us, so we can immediately get the eigenvalues because the solutions to the characteristic polynomial are easily identifiable when the polynomial is factored like this. So P of lambda is going to equal 0 when lambda is one of these values, 1/2, 2/5, or negative 1/4. So those are our eigenvalues. Let's just write them down here. Lambda equals 1/2, lambda equals 2/5, and lambda equals 1/4. And you may have already noticed this, but if you haven't, just pop back up to the original matrix and look at what the entries were. In particular, look at the entries on the main diagonal. We got 1/2, 2/5, and negative 1/4, and those were precisely the eigenvalues. So that should make the hair on the back of your neck stand up and make you wonder, is that going to always happen, or was this just a coincidence? And fortunately, this was not a coincidence. This will always happen. And in fact, it would be the same if the matrix were an upper triangular matrix. And so in general, if you have any triangular matrix, let's state this in general, the eigenvalues are going to be the entries on the main diagonal. So the eigenvalues of a triangular matrix will be the entries along the main diagonal. So sometimes finding the eigenvalues of a matrix is not so hard, in particular if it is a triangular matrix. Okay, so that's a nice little fact. And in the next clip, we'll start to look at ways to actually find the eigenvectors associated with these eigenvalues. Because, for example, in this example, we got the eigenvalues, but each one of those eigenvalues has a corresponding non-zero eigenvector. And that's quite often going to be what you're interested in as well. So that's what we still need to do is outline how to actually find those.